today what we're going to talk about are the fixed point theorems. Specifically, the lecture was made about Brouwer's fixed point theorem, but we're going to talk a bit about introductory theorems first on this lecture. So, okay, how many of you ever heard the intermediate, I'm sorry for my handwriting, value theorem?
It's taught on the MS 101.
Yeah, it is taught in the 101. That's great. Just to remind somebody, basically it tells you if there is some interval AB, and notice interval, the function f of x is continuous. It doesn't have to actually be continuous everywhere. It can just be continuous here. It would suffice. So basically, for any c that would lie on this interval between f of a and f of b, there would always be some e such that f of e is equals to c. So what does it mean in a simple language is basically you have some random points like say a, b, f of a, f of b, and if the function is continuous, you have to go through all the values here. Like you cannot just like skip them, because if you skip them, it's not a continuous function anymore, right? Okay, so that's a very intuitive theorem that I guess people usually understand, but it's a very powerful theorem because like you can do a lot of cool stuff with it. For example, you can look at some function and be like, oh, so it has like a negative point and it has like a positive value point. That means that there should be a point whose value is 0 somewhere. That means it has a solution. So that's how you usually prove that like all like negative power functions, polynomials, usually they all have like a solution. Why? Because of this theorem. So we'll just use that trick a lot today. So please try not to forget it in the first 5 minutes. Yeah, basically, intermediate value theorem was proved by Bolzano in 1817. But the thing is that he was using like a very rigorous proof, right? He thought he like so cool. But like one of the mathematicians actually think that his proof is not very rigorous and it's too vague. And so people had to like reprove it after. And then what happened to like a lot of theorems in analysis, like because people were treating infinity as something very simple, they actually underestimated how rigorous a proof should be. So we're actually going to talk about it a bit later, maybe like years 1, 2, or whatever. IBC is important for many reasons. Like I heard that Martin Gardner is like a very cool mathematician. Even proved that like if you're like you have like a very uneven ground and you have a table and you want it to like be stable, what you have to do is just like to turn the table around one leg and you'll finally find a stable position. I'm not sure that's actually true because it's like a legend, but like if anybody of you like whatever see a proof, you have to tell it to me. Okay, what we're gonna do is with help of this theorem, we're gonna prove Borsuk-Ulam theorem. So it's actually pretty easy. It's just stated this: if you have a continuous function f of x, then there always exists a point, say c, such that f of c is equals to f of minus c. And this theorem actually works for like n dimensions. So like if your c has like n components, it would still work. Like first, how would you prove that using this? Does anybody want to guess, or I just can show the proof immediately?
We just said it for the previous one, right? Like where you do that function, if you have one negative value and one positive value, then the third point will exist.
Yeah. So basically what you do is like, let's create some new function, say it would be g of x, and it's equal to f of x minus f of minus x, okay? So basically, because this function is continuous, its difference is also continuous. It's a continuous function. And because of that, we can see that g of x is this, but g of minus x is this. And that would mean that these two values are just opposite, right? Okay, but what it means is that there always should be a solution to this function g of x, right? Because that's what we did in the intermediate value theorem. We just proved that. And that would mean that there exists some c such that for g of c is equal to 0. And that would mean that there exists some x for which this is 0. Can you see that? Okay, great. So that means that there exists an x for which f of x equals to f of minus x. Done. So what's so cool about this theorem is like if you just think about its implications, it's just like it would just blow your mind. So like imagine like an Earth equator. Like you have an Earth, you have an equator, and basically what it tells you is there always would be some antipodal points on Earth. That means like they if you draw them, the line passes through the center of the Earth, right? There always would be some like pair of antipodal points which temperature is actually equal to each other. Like it doesn't have to be Earth. It can be like any sphere. So basically, that's like a very powerful theorem. Like, and you can do a lot of such stuff and prove very cool generalizations.
How do you prove that? Like,
For temperatures.
For temperature. Oh, okay, sure. So basically, you say temperature is a continuous function because I mean it would be weird if like this atom on the Earth had like this temperature, but this had suddenly a bigger one, right?
Yeah.
So it's basically continuous. And because you just state that C would be two-dimensional, so basically it means it has a coordinate. No, actually, okay. Let's say it's like two-dimensional. It has coordinates x, y, minus x minus y for this, minus c. And so basically, you'll be like, so it's a continuous function, so there should be some point c for which its antipodals are having a same have the same value for the function. Okay? Okay. So basically, you can go even further. If I'm not mistaken, you can actually prove that on the Earth there would always be at least one pair of antipodal points for which temperature and pressure are equal to each other. And that's actually a very cool proof I once saw somewhere. I don't remember where I saw it. But the sketch of a proof goes in this way. So you have Earth, we'll take an equator, and we already found with Borsuk-Ulam theorem that there are two antipodal points with the same temperature. Let's just mark them. So let's just take any two different antipodal points on the equator and just fix them. So we're just gonna turn our equator just a bit. We're gonna turn it. And we're gonna find another two antipodal points with the same temperature. And we're just gonna keep going like that, turn it until it reaches itself. And so basically what happened is that the point that you marked would make up, it doesn't have to be like a perfect equator, right? But it would be some kind of a loop around the Earth where all the antipodal points have the same temperature, right? And this is a loop, and this is a continuous function. So applying the Borsuk-Ulam theorem, if the pressure is our new function, there would be two antipodal points on this loop with the same temperature, and by definition they already, the same pressure, and by definition they already have the same temperature. So, like, say we found them, and yeah, here you are. Like, and that's, I think it really blows my mind, because like, imagine there's like a point in the Pacific Ocean where it would be as cold as in AB, and means somebody also suffers there. Like, it just makes my heart water, you know.
Well, but the Earth is not a regular ball, so there are on the surface.
Oh yeah, I mean, yeah, I'm
It's
sorry.
a
Like,
simplification.
yeah, it's a simplification. Basically, Earth is not like a very round ball, but like, I can just say it doesn't have to be like on the ground. maybe like I will just say that there is like a ball of like air around the Earth, and we can make it idealistically sphere, right? Because there would be like points with the same temperature somewhere not far away from the ground. So that's still okay, right? Okay. And yeah, for n dimensions, basically, the way you would phrase n-dimensional Borsuk theorem would be this. So we call a circle a sphere of one dimension. We call usual sphere a sphere of two dimensions, and so on. So if you have a sphere of n dimensions, and there is some function that maps points from the sphere to real numbers in n dimensions, that would mean that there exists some point c such that f of c equals to f of minus c. So basically we saw it, like, let's plug n equals to 2, that's the sphere, and that means our function should go from the sphere of the Earth to like real points in dimension 2. That means we're able to fix two variables like temperature and pressure. So basically, if our Earth would be 4-dimensional, there would be two antipodal points with the same temperature, same pressure, and I don't know, same humidity or whatever. I don't know, it just looks very cool to me. Like, because with this kind of proofs, you'll be actually able to prove a lot of facts that people would not actually think are very intuitive. I remember a professor I talked about, and he made his PhD based on just this cool facts. And there are a lot of corollaries to this. Basically, one of them is one of my favorite ones. It is called the ham sandwich theorem. I guess you know why I like it so much. Okay, the ham sandwich. Sandwich theorem. And basically, the way it goes is like that. You have a bread, then you have some layer of ham, and you have another bread. But let's just make those two breads like this, like different. Like say I put some sesame on it or something. Okay, good. That's our ham sandwich. And basically, me and my friend, we are not very good cookers, so we put it kind of in a very bad way, not in a very even way. Like just a bit more bread here, a bit more ham here, right? And so now we want to divide it with one slice of a knife, because we just bought it from a roommate, we have to return it very fast. And the thing is that we both like sesame, ham, and lower bread equally. That means we want, with one slice of a knife, cut it in a way that we would get the same amount of upper bread, of ham, and of a lower bread. And basically, the question is is that even possible? Because I feel like we can make very ugly sandwiches, you know? Maybe I can just put ham there. But the ham sandwich theorem tells us that basically if you have n objects in n dimensions, then you have an n-1 dimensional surface. That would cut those n objects in half each. And I mean I feel like that's very beautiful. You can find a lot of useful applications for it. Yeah, and another thing I wanted to show is the way you do it for pancakes. Yeah. So the problem with this theorem, even if it is very beautiful, it's actually not very intuitive, and I just lost my spot.
It's behind it.
Oh? Oh. No, it's not. Okay, never mind. So basically, thank you. Basically, what happens with pancakes is the same what happens with Ulam-Borsuk theorem, I guess, and with intermediate variable theorem. Is imagine you have two pancakes, This one is a chocolate pancake. Maybe that's kind of like a strawberry or something. So you want to divide them with a 1 cut. So you both get like the same amount of chocolate, the same amount of strawberry. And the proof would intuitively go like that. So imagine I divided this one more or less ideally. Like I made a slice through the center. And so this one are equal area of a strawberry pancake. But here I divided into like 1x, 2x areas. So basically what I can do is just to try to rotate it a bit. I mean, okay, second try. My next results are, I don't know, 6y and y, something like that. So now this area is bigger. And so if you look at it, 1/2 and 6, and somewhere in the middle, you'll actually be able to find a cut that goes through 1, because the cuts are kind of a continuous function, if you know what I mean. So basically that's how the proof for pancakes goes. The same proof would be able to apply for like n-dimensional objects, but of course it's a bit harder because you have to like move your knife like arbitrarily in n dimensions. So there are more rigorous ways to prove that, but they were a bit too hard because they require knowledge of topology. And I promise there will be no prerequisites for this lecture, so I'm not going to prove it. But what I'm going to prove is the necklace problem. By the way, are there any questions so far? Okay, great. That means I actually made a good job and made it understandable. So necklace problem. So imagine that you have a very beautiful necklace and it has 3 types of jewelry, like some sapphires, rubies, diamonds, whatever, right? That would be like sapphires, that would be like rubies, and they are somehow arbitrarily placed on the necklace, right? And basically, you and your partner that stole the necklace, you want to divide it so that each of you get an equal amount of sapphire, equal amount of diamonds, and equal amount of necklaces. Okay, but you're also very lazy, and you know cutting the necklace that's made of iron is very hard. So you want to make it a minimum number of cuts for any rearrangement on the necklace. Okay, so how many minimal cuts can you do? Any suggestions? Just like guesses. I want to guess. Tell me a number.
No, I didn't hear some question.
Okay, so basically, oh, 2? Close. Somebody said 3? Okay, because the answer is 3. Okay, so if you have 3 types of jewelry, then you'll be able to always cut it with 3 slices. Cuts, sorry. Okay. Basically, if you have n types of jewelries, you always would be able to cut it with n cuts. And just to make it accurate, when I say a minimum number of cuts, I mean we all understand that if we would be lucky enough, like our necklace would be just perfectly symmetrical, and we'll need only 1 cut. But we are talking about like the hardest case possible. That's what we call like a minimal number of cuts. Okay. So how would we prove that you actually can do it with n cuts? Okay, does anybody have like any guesses? At least how the proof may look like, whatever. Just like something we used before, maybe. Just maybe. Okay, so I guess the first problem that you strike was is that we were talking about continuous functions for the entire lecture, and I just give you a fucking discrete function. Like that's not even continuous, because you have those like special jewelries, and I did not allow you to have cuts for the jewelries. But how about we'll just generalize it, and I'll allow you to cut jewelries. So basically,
Then it's just like the ham sandwich problem again.
Yeah, it actually looks very like ham sandwich problem. So what we're gonna do, but the problem is that you cannot prove it with the ham sandwich, and I tried, because ham sandwich uses like, you know, continuous objects,
Yeah.
but here like
Yeah,
it's
if
kind
it
of
was
not.
continuous, then it is basically the ham sandwich problem.
Yeah. Okay. So basically, I would allow you to cut through the diamonds and sapphires and whatever, right? So how about we allow continuous cutting? But what is so good about continuous cutting with diamonds is that we know, for example, there are 4 diamonds. So most of you would get 2, ideally. Imagine that we finally found a way to cut them. So basically, there was some cut here, and there were like some other cuts. So like, this part was mine, and I got this piece of a diamond. But I need to get 2 pieces of diamond eventually. And that means that there would be some other diamond that maybe would be broken specifically so I can get the other rest of it. Okay, some people who really like rigorous proofs, there actually can be just like multiple diamonds, like broken to like pieces or whatever, right? But in the end, we always can prove that if you have those like pieces summing up into a whole number, why is it not? Like, why can I just like move all of them to this specific diamond and just move my cut here? And maybe just don't even cut here. And maybe don't even cut here. And if we had like another cut here, like that's my part, I'm just like putting it here and giving this all to the second person, right? So you'll be eventually able to shift all the cuts. So I get a whole diamond, and we all get an even number of stones. And we can do this logical operation and again. So we'll be able to prove that if we have a specific solution that cuts through the diamond, we always will be able to find a discrete solution for cuts. That's okay?
So if a continuous solution exists, a discrete solution must exist.
Yes.
Okay.
Okay. But what it gives us is that it gives us the word continuous. And it means we can't imagine. So how will we prove that a continuous solution exists? Basically, let's just say, so if you just think about it, let's say that's an interval 0 to 1. And people who were attending my lectures about like infinite games are probably very tired about like interval 0 to 1 because I use them all the time, but I'm sorry, that's math. So basically imagine that there is some solution in cutting, right? So basically I for example get this part, and I get this part, and my partner gets this and this part. So they have to sum up to 1. And they also have to be positive. So I actually always can write them down as an squared, c1 squared, b1 squared, d1 squared. Why? Just because I found the 1. Okay. Then what else can I do? Can I think about this as some point on a sphere? I mean, I can, right? That's a 4-dimensional sphere with radius 1.
Oh yeah.
Okay. So pretend that I draw you a 4-dimensional sphere with some point A, C, B, D as its coordinates.
I think if it is 4 dimensional, then it should be a power 3.
Sorry?
If it's 4 dimensional, it should be a cubed and b c cubed, b cubed, d cubed.
Wait, why?
I just guess.
No, it doesn't have to. Like, it's always squares. It's fine. We're fine. Okay, but okay. I mean, I can do cubes. Like, even if that's cubes, and I don't remember its formula, but even that's cubes, it would not. No, it actually would matter for me. It's squares. Like, I'm pretty sure that's squares. Like, yeah, I'm pretty sure that's squares. Because like for circle that's 2, and for sphere that's still 2. Yeah. Okay. I'm pretty sure that's squares. Okay. So basically we point with this coordinates. And now, if we just think about it, what we can actually take another point with coordinates minus a1, minus b1, and blah 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 blah. But we still get the same kind of cutting. So what would minuses for us mean? So basically, how about this? The value itself would just tell us when do we cut, but the sign would tell me to which person I assign the number. If it's plus, I'll assign it to myself. If it's minus, I'll assign it to my partner. Okay, so basically we just made a bijection between cuts and points on the spheres. Okay? Okay, that's a clear bijection. What can I do after that? I have a Borsuk-Ulam theorem telling me that if I have the sphere, I have and if my function is continuous, I can always find some a1, b1, c1, d1 such that f for minus a1 minus b1 minus c1 minus d1 have the same value. Okay, cutting here is a continuous process. I see somebody got it. Okay, and what it tells us is that it would be some specific cut for which, if I assign this to myself, this to my partner, this to myself, this to my partner, I'll get a specific value. I'll get a specific value, say a1 plus b1. But if I assign minus values to that, it means I'll assign this to my partner, I'll assign this to myself, I'll assign this to my partner, and this to myself. What would happen is that now my function gives me a value of c1 plus d1, but because there exists at least one point with this particular feature, there would exist such cuts that a1 plus b1 equals c1 plus d1. And that means that we actually got the equal amount of everything. So that means that we're actually done. Okay, any questions? Because I feel like I skipped through some steps and maybe they're not obvious.
So
Yes.
can you find the actual the point? Can you find the point of the cut exactly?
Oh, that's a very good question. Yeah. So what's
So you just prove that there is
yes.
a point.
Yes,
you can,
yes.
but-
All theorems that I stated here are existential theorems. They tell you about the existence of something, but they never actually tell you the algorithm about it.
So is it difficult to prove or is impossible?
Sorry.
Is
Difficult to prove.
an exact point to calculate, or it's just too difficult to us?
To be honest, I feel like it depends on the example. So basically, I remember I watched a video of like 3 blue, 1 brown, and basically to the video he attached a document, like a link to your research, and research was basically basing the whole research in like electrical engineering on this specific problem. Like this specific problem helped him like to somehow find a solution to his engineering problem. And I didn't go into details. Maybe you can read it after and figure out what it was about. But I feel like even if you don't know the cuts, it still have some useful applications.
I guess there must be some point you can work out, but you don't have to calculate them. You just need to guess, and maybe there exists, but
Yeah,
how do you
I
prove
feel
that?
I feel like for some beautiful cases, you'll actually what the theorem gives you is it gives you a minimal number of cuts, and it's already pretty good because like at least now you know what kind of cuts you have to look for, right? And after that, maybe you can just like start dividing cuts somehow randomly and just like trying to like move them a bit, like making an algorithm that would search for like nearby cuts and see if they actually match whatever you want. I guess that it would be possible for at least some good cases. I'm not sure if that's about all cases.
And then wouldn't the Rubik's Cube one where the problem to find the minimum number of turns to get a Rubik's Cube. Wouldn't that come under this set of problem?
Sorry, Rubik's Cube?
I know that there's the maths problem that the minimum number of rotations you have to make with the Rubik's Cube to get it from any state to the correct state.
I actually don't know the problem.
No, what is the minimum number of rotations you need in a Rubik's Cube to go from any condition, like any kind of mix-up, to the one color on each side?
Oh, okay, I see.
Would that be this kind of problem?
I actually don't think so. Cause like this is just about some fixed points. And you're talking about a fixed point when you have everything colored. But that's a very specific case, and you're not actually, I don't think you'll be able to use this particular theorem.
But you're
there.
basically dividing, like, instead of 2 people, you're just doing it for 6 sides. You're just dividing each color to each side, basically. So
Yes, but you not. How would you try to find a fixed point on a cube? And also, I feel like cubic Rubik is like not a continuous function.
yeah,
And
it's
I'm not
just
sure how to
fixed.
translate it into a continuous function.
Yeah.
But that's a very cool question. I really like it. Yeah, actually, like this talk was designed to be like very small because I knew you guys have a lot of homework, and I have a lot of homework too. So that was all. Thank you so much. That was actually a super question. I never thought about it.
Awesome.